All right, we're recording, so keep it G.
So you don't get to tell students to go to hell and die anymore?
Oh yeah, before you all run away, I need somebody who's kind of strong to crack my back. So I'll show you how. Got a world of pain in my back. All right, so today we're going to continue talking about guts, toes, and strings, and focus on theories of everything. So just generically, so a status check from where we left off last time. Remember that the Standard Model is a gauge quantum field theory whose interactions are based on the symmetry group SU3 cross SU2 left cross U1 hypercharge, and we talked about how various schemes for unifying those three forces in time in a gut theory, grand unified theory, either in the form of an SU5 group or an SO10 group. And there's more. You can certainly pick bigger and bigger groups that can accommodate, get off your phone, that can accommodate the Standard Model. The problem is the bigger your group, the more extra stuff that comes along for the ride, and if we don't see that extra stuff, you got to kind of explain why we don't see it, et cetera, et cetera. Of course, huh?
Did we ever come to a conclusion last week about whether we've been able to successfully create and measure a theory? No? Okay.
Well, we didn't conclude. We just, any and all of the unification stuff, which includes detecting the new things that would come along because of some unification scenario, is going to be at energies. So remember the energy scale at which I said the couplings unify when you had the supersymmetric correction? I can't remember that energy scale off the top of my head, but it's way beyond
16 GeV.
way beyond anything that we've been able to get to in colliders.
Just a little bit.
Okay, so so that's sort of the aim of grand unified theories. And then of course there is the problem child of gravity, which kind of has hitherto been sitting out here lonely and feeling left out. And so we now today turn to what arises if you start trying to fold gravity into the story. And so if you fold gravity into the story, then you're genuinely thinking about some kind of framework or theory where you're accommodating all of the fundamental forces of nature, and that's of course called a theory of everything.
Oh, I get it, Toe.
So really you can kind of generically define a theory of everything, which is really trying to take into account all of the fundamental forces. You know, the aim of grand unified theories is a little bit more modest, but for good reason, because it turns out that the framework where you do gut theories and the Standard Model calculations and you're ignoring gravity, all of these stories work out when you quantize them. And of course, gravity is the one where when you try and quantize, you get into problems. And we'll talk about those problems in a bit. So we're going to talk about theories of everything to start with. And actually, if you start surveying theories of everything, invariably, like the literature kind of guides you to string theory. String theory is the theory of everything. So to separate a discussion about theories of everything from string theory, I'm actually going to go back in time a little bit and talk about efforts to unify these things that predate string theory.
I'm trying to get Kellen to come.
Kellen misses out. Okay? All right. So how do we get gravity in the game? So let's remind ourselves, So let's remind ourselves of what these Standard Model things actually act on. So in the Standard Model, we have, for the electromagnetic interaction, we can kind of think of the electromagnetic interaction as U1 complex phase rotations. Of spinors. So it turns out when you write down the
Oh,
when you write down the Dirac-Lagrangian for a free spinor field, since the Dirac-Lagrangian for a free spinor field is actually involves complex spinors, then you can talk about multiplying those Dirac spinors by a complex number, which is equivalent, and then you have to preserve the inner product of the spinors, and so that complex number has to have unit magnitude, and that actually defines elements of U1. So invariance of a theory under these U1 phase transformations gives rise to electromagnetism. The weak interactions, we know, and you'll understand why I'm repeating all this in just a minute. The weak interactions, and we shouldn't separate these two things. We should really just talk about electroweak, but I'm just kind of drawing a cartoon version of this, a dumbed down version of this, if you will. After all, I mean, G1 complex phase rotations, come on children, you got this. And the weak interactions we can kind of think of as these SU2 left rotations of complex doublets. Where we, for example, have a doublet of the up and down quark, a doublet of the electron neutrino, et cetera, et cetera. And so what the SU2 transformations are doing are they're little 2x2 complex matrices that just multiply these things. And when they multiply them, they generally mix up components. And so they transform up into down and electron into electron neutrino and so forth. And then lastly, QCD is based on the SU3 gauge symmetry, or I should say the strong interactions, but we'll just leave it as QCD. Rotations of complex color triplets. And when I say the word complex here, what I have in mind is that you can create linear combinations of these things, and the coefficients in the linear combinations can be complex numbers. They don't have to be real numbers. Now, I kind of put rotation in parentheses because when we think of rotation, we think of spatial rotations, right? We take the cup and we rotate it in space, okay? These are not rotations in space. Okay, they're rotations on these little funky, abstract thingamajiggers. Okay? But I'm going to come back and kind of try and force that into a picture of rotations in space in a few minutes. But what we want to do at the moment is we want to say, okay, well, how, if at all, does gravity kind of fit into this framework? Is there any similarities between gravity and the fact that the other forces are all somehow based on a symmetry? Okay? And it turns out that the answer is yes. And for gravity, what we have is invariance under GL for R. Any questions? Of course. Yeah, where this stands for the general linear group in 4 dimensions with real coefficients.
4 dimensions like 1 plus 3.
Yeah, it's 1 plus 3. Okay, so you might say, what is the general linear group in 4 dimensions? It is literally the set of coordinate transformations in 4 dimensions. Okay. Well, it's the set of invertible 4-dimensional coordinate transformations. So like I can pick, a t, x, y, z set of Cartesian coordinates to parameterize my 1 plus 1 plus 3-dimensional space-time, or I could pick a different set, okay? And as long as I'm not doing anything stupid or degenerate in my coordinate redefinition, then the transformation from here to here will be described by an element of GL4R. Okay. So the action in this case, so we now see I'm getting confused as to what I've talked about with my senior design students and then what I've talked about with you all. None of my senior design students are present. So the action in this case, so there's actions for these things which we talked about in particle physics a lot. We actually wrote down those actions and their equations and motions and so forth. For gravity, it turns out that the action takes a remarkably simple form given the complexity of gravity. And it's just the integral over 4 space of the square root of minus the determinant of the metric of space-time times this quantity called the Ricci scalar, where the Ricci scalar is just built out of first and second derivatives of the metric. And I know a lot of this is very sort of highbrow, but I just want to show you how simple gravity can look if you vary this with respect to the metric, because the metric in here is the only degree of freedom. So the metric is, have I talked about this in Physics X? I don't remember now. I'm so confusing myself, because we're going to do all of GR next semester where all of this is going to like come before. Anyway, so so if I vary this action with respect to the metric and set the variation to 0, as we always do for classical equations of motion, I get an equation that looks something like this. And this is, of course, Einstein's equation in 4 dimensions without a source term. So this is the Einstein Hilbert action, and this is Einstein's equations. Okay, which of course secretly represent a lot of things. Yeah, 16 equations. Okay. Okay, so I've sort of now kind of laid out this nice picture where the 3 standard model forces are all based on symmetries. Gravity is based on a symmetry. But what is the differences? Well, the differences are, of course, this set of symmetry transformations acts on space-time. They're the coordinates in which we think of when we're describing where things are located in space-time, trajectories in space-time. These transformations are not acting on space-time at all. They're acting on these sort of abstract internal things. So what we can say is that the 3 sets of these act, so this guy, acts in space-time, and these act in an internal space, or what we often call an isospace. So it is a space, you know, it's 2-dimensional in this case, it's 3-dimensional in this case, it's sort of one complex dimension in this case, but it's not space-time. Like, we don't move through those spaces. But those spaces represent sort of degrees of freedom that are there, at least for this part of the theory. And so a question you might ask, and certainly was asked very early on, was, if I want to sort of unify gravity with the other forces, why don't we just make space-time
Internal.
bigger? Why don't we say there's more to space-time than just the 4 dimensions we can move in? If we add extra dimensions, then maybe those extra dimensions could somehow be these new internal space-times, okay? And then maybe if we're lucky, adding in enough extra dimensions, we can sort of get a clean theory that describes both gravity in 4 dimensions as we know it, plus all of these internal symmetries. Well, an important question to ask, of course, is, okay, if I make space-time bigger, what is the theory that I use in that larger space-time? Okay? And the answer, which is why this is an elegant proposition, is that, well, since you're just dealing with space-time, you're kind of getting rid of these abstract internal spaces and you're promoting them to actual parts of space-time. The theory that you should be using on this larger space-time is gravity, because gravity is a theory of space-time. So the idea is to simply look at pure gravity in a larger number of dimensions, which is an incredibly simple idea.
But it still only acts on those 4.
No. Gravity works in as many dimensions as you have, period. Okay? It is an incredibly simple idea that works out almost perfectly. except that it doesn't, and when it doesn't, it sucks, because it came so close, okay? So the idea is so simple, actually, that it was actually proposed shortly after general relativity itself was formulated. All right, so way back in the early part of the 20th century, Kaluza said, well, what if we just think about gravity in 5 dimensions? And so I'm going to kind of talk a little bit about that case because it's the simplest one. And in fact, at that point in history, early part of the 20th century, we really didn't know that much about these two. We certainly didn't know that they were based on internal symmetry groups with local field theories. We knew a lot about electromagnetism. People kind of knew about U1 as a symmetry group of electromagnetism. So the sort of historical story I'm about to tell you is dating back to, we knew about gravity and GR, we knew about electromagnetism. Let's see if we can at least get those two things unified. And then I'll talk about an extension later on to include these. Okay? All right, so our starting point for this discussion is going to be I just had the scary thought of somebody opening the door and clocking me in the head. I nearly got taken out in class yesterday. Were you in the first or the second discussion?
Second.
Second, yeah. In the first one, was it the first one? Was it the first one where the kind of tall guy held the weights?
Really hard.
I can't remember, but in one of them, some really tall guy held the weights, and I was spinning them on the platform. I kept almost walking into the weights as they came down, and I got myself killed.
Somebody did get hit.
Okay. So consider GR in 1 plus 4 dimensions. Okay? So we're going to consider GR, so the action is exactly what we wrote down over there. The difference being, of course, that instead of 4 dimensions, it's going to be 5 dimensions. And we're going to use the same action. Whoops. I call it big G for the metric of space-time for reasons which will become obvious in a moment, times the Ricci scalar. And again, this is just something that's built out of the big G. So the big G is the field. That's the degree of freedom in this theory. All right, so, and then what we're going to do is we're going to take the metric of 5 dimensions. So here I have in mind that A and B are going to be coordinates on 5 dimensions. And so those are going to take values 0, 1, 2, 3, and 5. For obvious reasons. And then I'm going to break it out. Let's break it down. Break it down. Wind that back. All right, so what we're going to do, this is a symmetric 5 by 5 matrix, right? All metrics are n by n matrices where n is the dimension of the space-time, and they're symmetric. Because we're thinking about a Riemannian space-time, which therefore has no torsion. If you introduce torsion into the theory, then you would have an antisymmetric component measured by the torsion tensor, but we don't have that. And so what I'm going to do is I'm going to take this 5 by 5 matrix and I'm just going to look at it in pieces. So I'm going to start by peeling off a 4 by 4 piece here, and I'm just going to call that G mu nu, where mu nu take values 0, 1, 2, and 3. Okay? The weird notation here is we are in 5 dimensions, but relativists have this really bad habit of calling time the 0th dimension. They're just labels. They don't mean anything weird. So when I want to refer to the 5th dimension, so I want to call it 5. But we got to call the 4 regular dimensions 0, 1, 2, 3. So that's the weird notation. So this is a 4 by 4 piece. This right here is, it's the 5th row, and then it's got 4 columns in it. So the indices here are row, column. So this, of course, has 4 rows and 4 columns. This is the 5th row, but it has 4 columns. And of course, this guy here is the 5th column, but it has 4 rows in it. And I'll call it mu, because the quantity that's labeling the rows in this thing should also label the rows in this thing, and the quantity that labels the columns in this one should label the columns in this one. And then this last booger over here is G55. I literally have not done anything deep or fundamental here. I've taken a 5x5 matrix and I've called various pieces of the different things. And then we're going to make an important assumption. And what we're going to do is we're going to assume that everything you see here, so remember in general relativity, the whole idea is that these things are functions of space-time. They can change values as you move around. That's very unlike non-gravitational theories where the metric can be written as a constant everywhere. The whole idea of general relativity is that these are functions, they can vary, and that gives you interesting curved geometries. But what we're going to assume is that all of these things are of this form. So what is the assumption that I've made?
Each of them only depend on the position in those first 4 dimensions.
Yes, exactly. I've assumed that nothing depends on x5. Everything's independent of x5. Okay? That's a very important assumption, but it does some magic for us. Okay? What magic does it do? The magic that it does is if we take the metric here, or the action here, since nothing depends on x5, I can integrate over that coordinate. Because everything is a constant with respect to that coordinate. Okay? So there's a step that I'm obviously not going to be able to do in detail where we integrate over that coordinate and we rewrite all of these things here in terms of these various pieces. Okay? And if we do it, we get something like this. And I'm being a little bit heuristic here and leaving out some coefficients whose magnitudes I don't know off the top of my head, but it's not that important. And I'm just going to call that thing R built out of the big metric G for the 5x5 spacetime. This is R built out of the little metric for the 4-dimensional spacetime G. Okay. Does that look familiar to anyone?
The F bit does.
What does the F bit remind you of?
Maxwell equation.
Exactly. This is the electromagnetic Lagrangian. It's in a form a little bit weird because this is the electromagnetic Lagrangian adapted to curved space-time. But you could take this to be a flat space-time if you want, in which case this factor just becomes 1. And this is literally the Maxwell Lagrangian, from which you derive Maxwell's equations as the equations of motion. Okay. This is a scalar field because G55, in terms of 4 dimensions, G55 is just a scalar. If you do transformations in 4 dimensions, they don't touch this. These things transform like vectors in space-time. You can see it, they have one space-time index, V or mu. So interpreting things in 4-dimensional space-time language, these become the vector potential of electromagnetism, this becomes a scalar field, and this of course is the metric of 4 dimensions. And so what we discover is that starting with pure 5-dimensional gravity, this was our starting point. Rewriting it, this is nothing here, this is just rewriting, and making this assumption, in 4 dimensions we are left with 4-dimensional gravity, electromagnetism, and some scalar field.
Nice.
Okay. This was the original observation of Kaluza and Klein. Well, this is the original observation of Kaluza, and then sometime later, Klein came along and said, well, I can actually justify this. Okay. So the justification goes something like this, and I've talked about this many times in other contexts, so I'll do it very quickly. And the idea is if I want to prevent things from depending on x5 in sort of degree of freedom language, that's saying I don't want anything to be able to move in the x5 direction. Everything is just fixed at a certain value in x5. And so the simple way to do that is to say, okay, if x5 is identified under some shift by a distance L, then what we discover is that the momentum in that direction, whenever we consider quantum mechanical theory, the momentum in that direction is going to be quantized as some integer over L. So this is literally the momentum spectrum of a particle in a box of length L. It's the same thing. You've seen this before in quantum mechanics. You'll see it in modern physics. Okay, and then the idea is for L really small, let me call this P5N. For L really small, N is really large for N not equal to 0. So what you can say is that as long as the size of this extra dimension is small enough, then no particle that we've seen or created could actually move in that direction. Okay? The only allowed momenta in the 5 direction would be the n equals 0, but that means you're not moving in that direction. Okay? So combining the idea of compactifying the coordinate, making the coordinate small, and then quantization of momentum means that we can effectively ignore that coordinate, at least in terms of things being able to move or depend on it. Okay? So the assumption is not just that we have 5 dimensions where we use gravity, it's really that we have 5 dimensions and we take the 5th dimension to be very, very tiny. Because that naturally enforces this, and the result is this. Okay? Okay, so that's the Kaluza-Klein mechanism in sort of its simplest form. But of course, it only folds gravitation and electromagnetism into the story, and of course, a theory of everything would like to incorporate both the weak interactions and strong interactions, so the natural next question is, can we do better? So what about SU3 cross SU2 left? Okay, so in order to figure out SU3 cross SU2 left, it's helpful to just think a little bit more about what happened here. Okay, so the first thing to note is that U1, so remember a U1 transformation is a 1 by 1 matrix, so that's a number, that's complex and satisfies C dagger C equals the identity. This is the unitary condition, and it's a 1 by 1 complex number, okay? And its determinant is +1. No, actually its determinant doesn't have to be +1 in this case, okay? So one way to represent a U1 is as a complex phase, e to the I theta, because we immediately know that if I conjugate that, e to the minus I theta, well, e to the minus I theta, e to the I theta is 1, so we're in luck, okay? But you are all probably aware from some context or another, either a math class or one of your physics classes, that one way to think about multiplication by a pure phase, pure complex phase like this, is a method of describing moving around the unit circle in the complex plane, right? Okay, so this is the method of phasors, if you've seen it in that context, but generally speaking, we can think about multiplication by a complex phase as moving around a circle in the complex plane. Okay? If you pick an arbitrary complex number, that's a point in this plane. And then if you multiply it by a pure phase, then all that does is it moves the number around a circle, okay, with the radius held fixed. So what I'm trying to get you to see is that this thing right here has a geometric interpretation in terms of a space, which is a circle, okay? Circles obviously come equipped with a compactness, and so we can think of the L that we used to make the size of the extra dimension small as just the circumference of the circle. Okay? And of course, this is a one-dimensional space-time. The circle itself is one-dimensional. We're looking at it drawn in 2 dimensions, but we only care about the circle itself. So the bottom line is U1 requires a circle, which is also called a 1D sphere. Okay? So then the question is okay, if I want to add in SU2, and I'm just going to call it SU2 for the moment. If I want to add in SU2, what kind of space do I need to add? So right now, for Kaluza-Klein, what we have in mind is we have our space-time is some 1 plus 3-dimensional space. I'm going to call it W because I don't want to call it M, which is Minkowski space. We're not necessarily on Minkowski space because this can be a non-trivial curved space, so I'll call it W. And then we've added an S1. That S1 is what allows us to get electromagnetism out of the story. So what about SU2? What kind of geometry do you think we need to add in order to get SU2?
2D.
Say it again?
2D circle.
A 2D circle?
Yeah. Or sphere.
So a 2-sphere?
Yeah.
Why do you say a 2-sphere?
Because it has a 2.
Because it has a 2? Okay, so well, let's ask. So this is complex, right? So you got to be a little bit careful because when things are complex, I should really think of this as having 4 degrees of freedom in it, right? It's a 2x2 complex matrix. Okay, but we're not adding complex spaces, right? Here we added the circle. I of course, am sort of connecting the circle to U1 through embedding the circle in a complex plane, but I'm not saying I'm adding a complex circle. I'm literally just adding a circle. So I would kind of like to get away from the complex idea here and get to something that's real. And then we can probably give it an interpretation. So is there any way you can connect SU2 to something real?
4-dimension.
4-dimension what? Oh, 4 real dimensions?
Yeah.
It's actually more than we need.
Is it SO3?
Yeah, exactly. So locally, SU2 is the same as SO3. This is a fact which you will exploit extensively in your modern physics, your first quantum mechanics class, because this is actually how we take rotations in 3-dimensional space, and we uncover the spinor representation of rotations in 3-dimensional space by the local isomorphism of SO3 and SU2. Of course, they differ globally. There's a double cover, but we're not going to worry about that. But the idea now is that this is real, but it involves 3x3 matrices. So do we need to add in a 3-dimensional space? So I would like to somehow get this symmetry by adding in an extra space. So what is SO3? It can be used to describe rotations in 3 dimensions. So if I want to fully talk about rotations in 3 dimensions, what sort of object do I need to consider?
2-sphere.
Yeah, I can think about a 2-dimensional surface, a 2-sphere. Okay? So in the fancy schmancy language of spaces and symmetries, we would say that we add in a 2-sphere, where a 2-sphere is, remember, the surface of a ball. It's not the inside, it's just the surface. We add in a 2-sphere, and the isometries of the 2-sphere correspond to SO3. That is, what can you do that won't change the appearance of the 2-sphere? Well, you can rotate it all around. Okay. Now, where it gets tricky is when we think of SU3, because we don't have this simple guy. Okay. It turns out that for SU3, there's not a simple way to do this, so I'm just going to give you the answer. Oh, and I should say, you can always do any of this with higher dimensional things. Right? I mean, I can take a 3-sphere, but this is not obvious. Well, actually, we'll do it this way. So I could, for this case where I had to introduce the circle, I could also have introduced for this case an S2, because an S2 is invariant under rotations in a plane. So I could always add in a higher dimensional space, but in order to capture this symmetry, the smallest space I can add in is just the circle itself. Okay? And then similarly here, it's hard to visualize, but you could introduce an S4, or sorry, an S3, which would have invariance under SO4, and then you could accommodate that SO3, but anyway, we don't want to go there. All right, so for the SU3 case, it turns out that this would require sort of the smallest dimension realization of this is something called CP4, which is complex projective space. And do you guys see complex projective spaces at all in any of your classes?
Not called that.
Okay, so I'm gonna give you a really quick and dirty on the simplest projective space, and then I'm just gonna let your imagination run wild with what CP4 might actually look like, because I'm sure as hell ain't gonna draw it. So the simplest projective space is to take the XY plane and say, okay, any point in the XY plane is of course given by an ordered pair XY, okay? And then what the real projective line corresponds to, this is a real, because I'm not looking at complex numbers, the complex plane, and it's projective for the following reason. What I'm going to say is, I'm going to say that any point XY is identified with any other point which is related to it by a constant multiplier lambda. Okay, so what does that mean? Well, you can just kind of think of it in terms of vectors. If I draw a vector from the origin to the point xy, what is this thing?
Any multiple of the same vector?
Yeah, it's a multiple of that vector, which means it's any shorter vector, any longer vector, or any vector going this way. Okay? So this is an example of an equivalence relation. And what I do with an equivalence relation is I say, all things that are related in this way, I am going to call the same thing. Okay? So what we have in mind is that if I pick a point, I am actually choosing the collection of all points along the line goes from that point through the origin out the other side. Okay? So here's a simple question. What does that space of objects look like?
A line.
It looks like a line.
Yeah. I mean, the way you draw.
What does the collection of objects look like? If I were to try and beat it into something I could see. So what is an object in this case?
It's just lambda.
So an object is an equivalence class. So this line is an object.
Oh.
Because all of the different versions of this point are the same thing. So what's a different object? Who can tell me what a different object might be?
Different line.
Yeah, a different line. So I can take a different point and do that. Okay? So how many of these, or what does the collection of these equivalence classes actually look like? Like, what does it flesh out?
It's a circle.
The space.
It's almost a circle.
It's a circle that goes things.
Quarter circle.
Almost.
8th circle.
So one way to sort of identify things is to say, if I draw a circle,
Oh, 2nd circle.
then if I pick a point on the circle, then that corresponds to one of these things. But of course, the antipodal point on the circle also corresponds to the same thing.
Nice.
So what I can do is I can start here, And I can draw the circle up to, but not including this. And this object represents the collection of equivalence classes that I'm talking about. Okay? I don't include this because this is actually the same as that. And then anything up here corresponds to something down here. Okay? So this thing is called the real projective line. It's defined through this relationship, and it's a one-dimensional space. Okay? Everybody on board with that? All right, now we can obviously change the story. We can, instead of thinking of the real plane, we can think of the complex plane. Okay? And it turns out that if you want to define CP4, then what you can say is, I'm actually going to CP4, and I can't remember why it's called CP4 off the top of my head. It is CP4. Oh, I'm sorry, not CP4, CP2. And I don't know why it's called CP2. Sorry, CP2. But the definition of CP2 is that I take, no, I know why it's called CP2. I'll come back to you in a minute. But the definition of CP2 is the following. I'm going to take a triplet of things, but each of those things are complex. Okay, so X has a real and imaginary part, Y has a real and imaginary part, and so for Z. And then I'm going to define an equivalence relation that says XC is the same as lambda XC, YC is the same as lambda YC, and ZC is the same as lambda ZC for any real lambda, or for any complex lambda. Okay? Oh, I should say in all of this, in this definition, you have to start with the plane XY, but you have to remove the origin, because none of this works if you include the origin. Okay, so same here. You remove the origin from that sort of product of three complex planes, and then you define this equivalence relation. And it turns out that after you define this equivalence relation, if you actually try and identify what the resulting space looks like, which is obviously much harder because it's a higher dimensional thing, it turns out that this thing is a 4 real dimensional space. Okay? CP2 being 2 complex dimensions. Okay, but it's got 4 real dimensions to this space. Right? Now, I want you to think about it for a minute, though, because why in the name of Christ would SU3 somehow be affiliated with CP2? Like, can you even see where SU3 might enter into that story? Like, we've got 3, and we've got 4, and then we got 2, and we got all these numbers floating around, and why CP2 somehow being connected to SU3? Like, well, look at it. This is a 3 complex dimensional object. If I thought about doing some operation on it, I would use a 3 by 3 complex matrix, which is exactly the starting point for SU3. Okay. The fact that this ends up giving you a real 4-dimensional space is just sort of an artifact of tracing through what this equivalence class does and the resulting space that emerges. You know, and it's not obvious. Like, here we started with 2 dimensions, and through the equivalence class relations, we ended up with a 1-dimensional space. Okay, so the bottom line of all of this is that in order to accommodate SU3, we need at least CP2, which is a 4-dimensional space. Okay? So overall, how many extra dimensions do we need? 7. What's 7 plus 4? So in order to get the entire standard model from a Kaluza-Klein type mechanism, and by the way, in all of this, I have sort of relegated myself in these two cases to simple dimension counting. I haven't even tried to argue that somehow the symmetries, well, this thing we know, the symmetries of a two-sphere have SO3, which is equivalent to SU2 invariance, and so it kind of makes sense that the Kaluza-Klein theory would give you that symmetry. This one, it's not obvious that CP2 has an SU3 invariance, but it does. But anyway, going back to the counting, what we discover is that in order to get the three standard model forces out of the Kaluza-Klein mechanism, that is adding extra space-time dimensions and then assuming they're small, you need to work in at very least 11 total space-time dimensions. The number 11 is incredibly special. Okay. It's what? You guys, killing me. The number 11 is incredibly important for reasons which we are clearly not going to get to today. But this number will pop up in a lot of other situations. And so one might be led to think, oh man, this is actually a beautiful story, because we know from other angles, and I'll talk about those in another talk, that 11 is a special dimension of space-time for other reasons. Here, to get the standard model from the Kaluza-Klein mechanism also requires 11 dimensions. Maybe this works, and then it turns out that it doesn't. And we blame this, as many things, on Witten, who in 1981, I believe, argued that this in fact does not work, because as it turns out, the Kaluza-Klein mechanism gives you SU2. That was the entire argument here. So it gives you an SU2 gauge theory, but of course we know that SU2 gauge theory is not what's in the standard model. What's in the standard model?
SU2 left.
SU2 left. That is, the SU2 symmetry of the weak interactions only acts on left-handed components of these fermion fields. And what Witten argued is that you actually, from the Kaluza-Klein mechanism, you always get gauge interactions which act equally on the left and the right. You get a pure SU2, not an SU2 left. So as nice as the idea is, and as sort of clean as a lot of it works out, and it does work out really cleanly, this little bitty L right there screws the pooch. Yeah.
If we find a right-handed neutrino, are we going to jump back to 1981?
No, finding a right-handed neutrino doesn't suddenly make the weak interactions SU2 left cross SU2 right.
Okay.
The existence of a right-handed neutrino is a separate question from what is the form of the electroweak interactions. That's a point that a lot of people get really confused about. So just because you find a right-handed neutrino doesn't suddenly mean that these interactions get promoted to a full SU2. Okay, and yeah, I'm not going to go much further into that right now. Okay, so now you might say, oh, this sucks, screw you, Witten, you screwed up Kaluza-Klein for us. It's okay, because it turns out that Kaluza-Klein is actually going to be an important part of the story anyway. It's just not going to give us sort of the minimal answer to how do we combine the standard model forces with gravity. It would be elegant if it could happen just through pure higher dimensional gravity. But it turns out that there are actually deeper problems with the idea of combining gravity with the standard model forces. In particular, one thing you will notice I have not spoken about at all is quantum, is really quantum versions of these theories. I made the little argument about momentum being quantized in a small direction, but if I actually ask, what does this quantum theory look like? Because this is purely classical. When we actually start asking and answering that question, we find that this entire program is a bit screwed from the start, and we're going to have to find a new beginning, and we'll talk about that next time. We might get done with this by the end of the semester.
You actually, are you done for today? Because you actually finished.
Oh, actually, no. You know what? That was like my mic drop, because I was sure I was going to turn around and look at the clock, and the clock was going to be like 5 minutes after. Okay, so actually, I'm going to pick the mic back up. We'll return. So we'll return to this, and I'll I'll set the stage for next time. Okay, so I'll set the stage for next time.
Because you can't just finish on time, you have to finish 5 minutes late.
Basically, yes.
You know what word starts with sh?
Shush.
Shadow.
That's 2 words. He's got a point.
Okay, alright. Alright, so, aren't you sad you're leaving town?
Are you gonna lecture that Tuesday?
Shouldn't I lecture the Tuesday before Thanksgiving break?
Wow.
Thanksgiving special.
Huh?
Thanksgiving special.
Thanksgiving special.
I expect you to bring in a turkey.
Yeah, I'll be gone.
We'll,
Bye.
we'll assess the population and decide it from there on.
Oh man, I am.
Okay, so, bigger problems. So this whole idea is nice and elegant, but it's screwed because what we discover is that if we have any theory where we sort of unify standard model and gravity, of course that makes everyone happy, that's the theory of everything, we get smiley faces. But when we add true quantum mechanics, when we try and quantize this, what we discover is, of course, that the standard model is perfectly happy to be quantized, but gravity doesn't quantize so well. Okay? So what is the problem with quantum gravity? So there's actually several different ways that you can see problems with quantum gravity, but the sort of classic answer to this is as follows. I alluded last time to the idea that quantities get renormalized. Couplings run in theory, so we plotted the coupling constants in the standard model versus energy scale, and we found some nice behavior, and then it corrected with supersymmetry, and they actually met at a point. So the question one has to ask when you do a quantum mechanical theory is, can you actually put this program into place and actually make sense of how things are running with energy scale? And it turns out you can run into a very significant problem in the following way. So in a quantum theory, so first of all, in a quantum field theory, which is where these problems actually crop up, in a quantum field theory, we often encounter divergences. Okay, so we have a quantum field theory, it's specified by some action, and we can use a path integral to quantize it. And then when we start computing actual values for things that we might compare with experiment, what we often find is that those quantities start getting infinite. Okay? So for example, if I calculate the charge of the electron, the charge of the electron I can kind of think of in a quantum field theory calculation as the strength of the strength of the interaction between an electron and another electron. So if I just thought about this as a charge Q particle, the larger the value of Q, the stronger these things couple to the photon. That's the carrier of the electromagnetic field. And so the larger the charge, the larger this interaction, and the more pronounced the effect. And so for example, if I took this to be charge 0, then this diagram wouldn't even exist, because if you don't have any charge, you don't connect to the photon. Of course, we know fundamental particles are quantized in units of the elementary charge, but let's just for a moment pretend we could shift the value of Q. And the problem is that this is not the only diagram that contributes. We know that you get corrections from all of these higher order diagrams. And what you discover is that all of these added together give you the overall effective charge between two objects. And unfortunately, what you discover is that diagrams that involve loops like this can give you infinite contributions to the calculation. And so when you actually include the quantum mechanical corrections in determining the value of, say, the electron charge, you find that the answer is infinite, which is slight mismatch from experiment. Okay? So what do you do when you've got a theory that otherwise seems to be pretty good, but it's predicting infinite values for charges and also infinite values for masses? What you do is you say, well, okay, wait a minute, what did I start with? So what I started with was, Maxwell, electromagnetism as we know and love it. And then we quantized the Maxwell theory. Okay? So the Maxwell theory would be, if you were doing a quantum field theory thing, it would kind of like be the initial value, and then these things correct the Maxwell theory. They give you these sort of quantum corrections to the Maxwell theory. But we are actually completely misguided, because what we should be thinking about is that the Maxwell theory is sort of that whole thing lumped together, where we don't actually, because Maxwell's theory includes quantum mechanics, right? I mean, when you do it's like general relativity, right? The book falls. I'm looking for something to drop. I'm not finding very much. The book falls. Is that described by Newtonian physics or general relativity?
Both.
Both. Okay. In general relativity gives you the answer. If I drop the book and I say, do I use classical physics or quantum mechanics to get the answer? What do I do? I can do both. I can do quantum mechanics and get the answer. So our observations of physical phenomenon automatically include the quantum effects. So what we should be really thinking about when we think about Maxwell's theory is this final answer that includes everything. How to get solar energy, that's cute. Anyway, so the point though is the charges that appeared here, and sorry, I should say this is Q effective. The charges that I'm putting in these diagrams are different than the charges that emerge after I add up all these contributions, but which one of those is the charge that I actually put in Maxwell's equation, or that appear in Maxwell's equations? It's these. Okay? So that then leads to the question, well, what the hell are these? What are the charges that appear in this diagram? Well, these charges are what we often call the bare charges. That is, these are the charges that you would see if you could get infinitesimally close to the electron. Get rid of all of the shielding of things around it, like virtual electron-positron pairs. Okay? And literally get to an arbitrarily small distance to the electron and say, hey, electron, what's your charge? Okay? Can we do that? No. We always have to view the electron from a distance. In fact, if we look at the electron from a meter away, we're effectively looking at the electron from infinity, because a meter basically gives us the same answer as infinity. And so the value of the electron charge that we look up in tables and books and so forth is actually the value measured at infinity, which is the value that you see here. The point is that we have no access to these numbers. So what we can do is we can say, and this is the crux, if you haven't been following anything, follow this. The infinity arose when we took these things to have the values we measure in the lab. And then we add up all the contributions. And we got an infinite effective charge, which makes no sense. Really, what we should do is we should take these to be the values that we see in the lab and work backwards to figure out what these values need to be. And it might turn out that these values need to be infinite, but that's okay, because we literally have no way to argue that they shouldn't be. We can't measure them directly. Okay? So the idea of renormalization, or the renormalizability of a theory, is that you encounter infinities, but you can redefine the quantities that you're working with so that you get a physical value and you get an infinite, or sorry, you get a bare value, no, you get a physical value, and then you get an infinite, no, you get a bare value and an infinite correction.
Just pick one, fix it in post.
Yeah, I'll just, there you go. No, in post editing, we will fix this combination. So, yeah, I mean, actually, I think there's a lot more details to this story, which I actually covered in the last lecture of the particle physics class, I believe. And so I'm not going to get the words right in this moment. But generically, what you do in order to generically what you do in order to actually tease out what's going on with this infinity is so you have momentum in these loops, and then you cut off the integral on the momentum. You let it go from 0 up to lambda, because in principle you integrate over all momentum values. And so you keep in mind this high cutoff on the momentum lambda. You extract various calculations, and then what you hope is that your calculations end up with some momentum cutoff dependent piece, and then some leftover finite piece. And then you take the cutoff to infinity, this thing goes to infinity, and we're left with some finite piece left over. And so this would be the actual G bar if we did the calculation. And so we can just say, we actually don't know what, we don't actually care about this thing per se, or even this thing per se. All we care about is that there's a finite piece left over because we measure finite values for these quantities. Now, if you apply this reasoning to the standard model, this all works out perfectly. All of the couplings, masses, and so forth in the standard model exhibit this behavior. Okay, so effectively you could say if something is appearing to be infinite, it's because I was stupid and I used a bare value which I don't actually have access to. If you apply this reasoning to gravity, it doesn't work. So if you try and renormalize gravity, you find that things don't split up in this nice way. Okay. Now, that used to be a really significant problem. In fact, the way that people used to look for fundamental theories of nature is they said, well, then infinity doesn't make any sense. Renormalization kind of gives us a way around it. So maybe in looking for fundamental theories of nature, we should only look for theories which are renormalizable, because those are the only theories that make sense with quantum mechanics. And so for a long time, people just looked at quantum field theories which were renormalizable, always knowing that gravity was not going to work out. Okay? And then in the 60s, a guy named Kenneth Wilson came along and he's like, no. That's not the way you should be thinking about it. What Wilson said was, the way you should think about it is as follows. Even if a theory is non-renormalizable, what you can say is that, and again, this is all covered in that particle physics lecture, so I'm not going to try and get into details, but what you can say is that the theory that I'm using to describe things is valid up to some scale, like lambda, some high energy scale. And the infinities I get are what happens if I take the theory I'm using and I extrapolate lambda to infinity. But what Wilson said was, in many cases, and this happens in actually very well understood cases, you have a description which is valid up to some scale, but then beyond that scale, you actually have to use different degrees of freedom. So as an example of this, okay, if we take a solid and we look at very low energies or very large distances, we can approximate it by a continuum. And you can use a continuous field theory to describe the physics of that, but if you start probing that continuous field theory up to a certain energy scale or a certain distance scale, you expect that continuum description to break down, because the truth is underlying that continuous thing is really a discrete atomic or molecular lattice. So the theory is, the fact that the description you're using is breaking down at some scale is telling you, hey, at that scale you should actually be thinking in terms of different degrees of freedom, something more fundamental. So in what's called the effective field theory framework, which is really what Wilson pioneered, and it's the way we think about these things now, the way we think about the problem of non-normalizability of gravity is that this is telling us that gravity is only going to be correct up to a certain energy scale, Below that energy scale, we're free to use all of this quantum gravity description. But beyond that energy scale, something else has to come into the story. In fact, there's a certain sense in which the fact that the standard model works all the way up to arbitrarily high energy scale is just weird. Because we expect that at some high energy scale, gravity is going to be replaced by something different and more fundamental. So why wouldn't you also expect the standard model to get replaced? Okay. And so that's what we're going to talk about next time, is what could possibly be the thing which, beyond a certain high energy scale, you have to rewrite the degrees of freedom, okay, which you previously thought was just some naive quantum theory of gravity based on the Einstein Hilbert action. All right, we'll talk about that next time.
I am gonna miss this one.
It depends on whether we do it next time or not. We have to decide whether we're going to meet Tuesday. Who's going to be here Tuesday of next week?
Yeah, so
It's just you.
it's just me. You could always Skype me in.